Alright, here we go on a video of the fundamental theorem of algebra. So before we get started, I would like you to just warm up really quick, and I would like you to solve these three equations we have here. We have a line and we have two quadratics. So you're going to need to just solve for x in the first one, and in the next two you're going to have to factor and solve. So get going. Pause the video and factor, solve for x for those three warm-up problems. So the first one is just 2x plus 3 is equal to 13. So you get x equals 5. Now, what we're going to be looking at here is not just what the solution is, but how many solutions can you have from a particular equation. So we have 2x plus 3. Notice we have 2x. It's x to the first power. X to the first power means at most you can have one solution. If you were to think about this graphically, it's just going to look like a line that goes something like that, and it crosses the x-axis once. That's why you have one solution. Now in the next one we have quadratic, x squared. So at the most we can have two. Notice it's at the most, doesn't have to have it. So we have a graph here, and it's going to look a little something like this. And you can see it crosses the x-axis twice, which means you have two solutions. And then the last one is an example of when I say at most, because it's x squared, but when you solved it algebraically, you see you have just x is equal to -2. And that's because we have x plus 2 and x plus 2, so it's known as a double root. So the graph looks like that. Okay, now, of course, you could also have no solution, and that's just the fundamental theorem of algebra is this is the most number of solutions you can have in any equation. So this next one, we have 4x cubed plus 6x squared plus 7. How many solutions do you think it will have? Now you're going to guess, and let's say you guess 3. If you guess 3, you have a good chance of being right. However, for this particular equation, you only have one real solution because your graph looks a little something like that. And the only time it crosses the x-axis is right there. And of course, we know how to use our graphing calculator to go back and find it. We will have a review on that shortly. So how could this graph also have looked? Well, it could look like it has two solutions. An example of an x cubed that has two solutions would be a little bit like this, where it crosses once and then bounces off once. And we could also have three solutions. An example of a x cubed that has three solutions would just look something like this, where it crosses the x-axis 3 times. So in this particular example, though, you only have one. That's just what this equation looks like, but there's no way it can cross it 4 times. And in x cubed, there really isn't a way that it could cross the axis 0 times, and that's because it's an odd function, which we will talk more about later. Different types of polynomials and their examples of. So if it has a degree of 0, that's known as a constant. And that's just a number. A degree of 1, that's a line or linear. And an example of that is just 2x plus 3. If you have a degree of 2, that's an x squared. That's known as a quadratic. An example of that would just be 3x squared plus 7. A degree of 3 is known as a cubic. And that would be -4x cubed plus 2x plus 5. These are just random examples, of course. And it's all based on the highest exponent of your variables. And then finally, a degree of 4 is called a quartic. And that's something like 2x to the 4th plus 3x plus 5. Those are just examples. I'm not going to make you memorize anything above that. However, if I tell you that something is a quartic, you need to know that that is an x to the 4th power type of graph. Okay? So let's move on to a new topic called end behavior. So before we get there, I want you to just know a couple of different terms. Standard form is when we rearrange a polynomial in descending order. So anytime you're given a polynomial, if it asks you to put it in standard form, you write it in descending order. That means starting with the highest exponent, so x cubed, then work your way to x squared, then x, and then your constant. That's called descending order. We don't want to say 5x plus 3x squared minus 13x cubed plus 7 minus 13x to the fourth power. Descending order, we start at the highest exponent and we work our way down. Intercept form is factored form, and we have already done plenty of factoring in this course, so you know what that means. So now we're talking about end behavior. Now, end behavior is a brand new topic for you, and this is what is the graph doing at the ends, meaning to the left and to the right. Normally, we say when you're looking at the arrows, what is the graph doing? So every time you write end behavior, it's going to start out with what x is doing. So as x, and we draw a little arrow, and that means approaches negative infinity. What that's saying is, what is this graph doing as it goes to the left? So look at this graph going to the left. What is your graph actually doing? Is it going up or is it going down? So if we look at this, as we look to the left, this graph is going up. Like I said, you pay attention to the arrows. So that means the function f of x is approaching positive infinity. So when you look at these graphs, basically you're saying as it goes to the left, is it going up or down? As it goes to the right, is it going up and down? So if we say negative 10, that means it's going to be a much higher number. If we say negative 1,000, that's going to be way, way, way up high. So as we go to negative infinity, as far as we go to the left, what is the graph doing? It's going up and up and up. And then you will say, what's the graph doing as it goes to the right, also known as positive infinity. So as x goes to positive infinity, what is the graph doing? And the graph, as you go to the right, also known as positive infinity, as x gets bigger, so does the graph. It's going up. So the graph is going to positive infinity. This is how you write your end behavior. This is the notation you will use. So the nice part is you just really need to think about what the graph is doing when you go to the left and when you go to the right. It's not nearly as confusing as it looks. So for the next example, we'll go through the next example. Again, we're going to say what x is doing as we go to the left, negative infinity, and what is the graph doing as we go to the right, positive infinity. And then you're going to say, what is f of x doing? So that's pretty much it. Now you just have to tell me what the graph is doing as you go to the left and as you go to the right. As you go to the left, you see that we go down. So that means this graph is going to negative infinity. As we go to the right, as x approaches infinity, the graph is going up. So it is going to positive infinity. All right, so I would like you to try the next two on your own. Pause the video. Remember, this part right here is going to be the same for both. That's just the notation. You just have to answer these questions. Okay, so go give it a try. And let's see if you got them right. So this one, it's going down both to the left and to the right. So for your f of x, they should both be going to negative infinity. And in this last example, as you go to the left, your graph is going up. And as you go to the right, your graph is going down. So as you go to the left, your graph is going to positive infinity. As you go to the right, your graph is going to negative infinity because it's going down and down and down forever and ever and ever. That's where the arrow is pointing. All right, so that's end behavior. It's not nearly as difficult as the notation looks. It's pretty simple. As you go left, where do you go? As you go right, where do you go? So 3 steps for these next two. I'll do the first one with you. We want to write it in standard form first. Remember, standard form is descending order. Highest exponent we have is x cubed, so we have a 3x cubed. Then we go to 4x squared. Then we go to minus 2x plus 7. We're decreasing as we go along. State the degree, the type, and the leading coefficient. So the degree is 3. And then the type is a cubic. And then your leading coefficient is the very first number in this after you put it in descending order, which is 3. Okay, and finally, C is state the end behavior. Now, I'm going to teach you a little trick. If you have an odd function, and we're going to go back and look at this for a second. If you have an odd, meaning the degree is odd, you are going to do something like, I'm going to back up for a second. These two on the right, these are both odd functions. Okay, these are odd functions. How do we know? Because as you go to the left and to the right, they're going to go in opposite directions. So if this one's going down to the left and up to the right, that is going to be an odd function. This one's going up to the left and down to the right, that is an odd function. So if you have a positive odd, or x to the odd, when it's positive, your graph is always going to start low and finish high. If you have a negative x to the odd power, your graph is always going to start high and finish low. So, for this example right here, we have a positive odd function. So we know as x goes to negative infinity, this is going to go down, starting low. And as x goes to positive infinity, the function is going to go to positive infinity because it is going to finish high. Now, you do not have to do it like that. You have a graphing calculator. All you have to do is type this in the graphing calculator and you will see that it looks like this, and you can just answer it by looking at the graph. But if you're slick enough, you can just look at the actual equation and figure it out from there. So, the next one's on you. Pause the video and you try number 2. And let's see if you got it right. Here's your descending order. It is a 4th degree, which is quartic, and it has a leading coefficient of a -5. And here's your end behavior. And as it goes to the left and to the right, it's going down, so we're going to negative infinity for both. Now again, there's a shortcut if you want to be slick. If you have a positive x to the even power, like this is an x squared, then it's going to go up both to the left and to the right. So it's always going to be going to positive infinity. If you have a negative x to the even power, it's going to be going down both to the left and to the right. So again, it's a shortcut. If you're answering a question like this, you don't have to pull out your graphing calculator and type it in unless you really want to. All right? Almost done. One last topic of this video. And this is just multiplying. So this is where I give you the zeros or the solutions to a polynomial, and you tell me what polynomial it came from. So this is just backwards factoring. Normally I give you the function and you have to factor it, and then you have to set it equal to 0, and you have to solve, and you get your solutions. Now we're just doing it the other way around. So it goes a little bit like this. We have x equals 2, and we have x equals a -3. And now we just work backwards. So where did those solutions come from? That came from an x minus 2 equals 0, and an x plus 3 equals 0. So where did we get those? Well, we got that from a factored polynomial that looks like this. And now all you have to do is FOIL. So you multiply x and x and x and 3, -2 and x, -2 and 3, and you're going to get your x squared plus 3x minus 2x minus 6. All we did was FOIL, combine your like terms, and you must put an f of x in front because it says write the polynomial function. So f of x is equal to x squared plus x minus 6. That's it. That's all you have to do. So in the next one, think about where a 1/2 comes from. So we have x equals 4, and we have x equals 1/2. So x equals 4 came from x minus 4 equals 0. Where did this come from? This came from 2x minus 1 equals 0, because you would add 1 to the right and then you would divide by 2. So that's where 1/2 comes from. So now we have a x minus 4 and we have a 2x minus 1. You're going to FOIL again. So you're going to have a 2x squared minus x minus 8x plus 4, which is going to give us f of x is equal to 2x squared minus 9x plus 4. And we're good. So that's it. Writing a polynomial function given zeros is just foiling. You just have to think about where they come from. It's just working backwards with something you're very familiar with. So, this next one. Pause the video and see if you can figure out where all three of those terms came from. And then we'll go through the rest. So, x minus 2 came from an x plus 2. A positive 3 came from an x minus 3. And a 0 comes from just x equals 0. So it just comes from x. And now you're just going to FOIL and distribute your x. And you're going to finish. So we're going to have an x squared minus x minus 6 after we FOIL those together. Now we need to distribute an x. So we have f of x is equal to x cubed minus x squared minus 6x, done. Now the last one's tricky. We know that 3 comes from an x minus 3. But where do you get a plus or minus 2i? So think, how do we get an I in the first place? It's when we take the square root of a negative. So where did 2i come from? That was when we had x squared is equal to a negative 4, because we had to square root both sides. You can't take the square root of a negative, but the square root of 4 is plus or minus 2, and that's how we get our plus or minus 2i. So where did that come from? That came from x squared plus 4. And now again, you're just going to FOIL, so you're going to get f of x is equal to x cubed minus 3x squared plus 4x minus 12, and that's it. So, a lot of stuff in this video. You have to know the fundamental rule of algebra. You're going to have to know some end behavior, degrees, descending order, and then, of course, how you write a polynomial when I give you the zeros. All right? So, that's it. This is video number 2 for this chapter. This is Longo, and I am out. See you. Bye.